We'll talk about combined physical and link layer protocols for quantum networks.
Yeah, we are basically from the application side of things. So all of these physics talks, we try to integrate them somehow into a network and also come up with some applications how we can use it. Let's first talk like purely from a network perspective, because we have to do abstractions, right? We cannot have the full physical models and so on, and also the full physical devices that there are. We cannot integrate them into. We need to integrate them into the network, but we cannot kind of consider them all the time. So just from a network perspective, what is kind of important for us. So we have some photon sources, which basically generate, for example, atom-photon entanglement or photon-photon entanglement. These are basically our generation devices, which we can generate the entanglement. Then we have a photon detector. In our case, it's really simple. We just have some I don't know, some plate or so that kind of records was there a detection or not with this click or not. Then we have some quantum channels, could be optical fiber, could be free space or so, where we put a photon in, for example, and we get a photon out. This can then be either, for example, absorbed or not, or we can have some disturbances to the state of the photon. And then we have quantum memories. The biggest obstacle, in my opinion, for the large-scale quantum networks and also the future networks that we have. So we need to be able to put in qubits, usually atoms, and then we also need to be able to remove them from the memory or somehow use them. Usually when we're talking about memories from networking perspective, we talk about input-output. Could also be that the atoms just stay in the memory and we can then perform some gates, for example, measurement or some amplitude or phase flips to the qubit. To get to what is heralded entanglement, this is basically one of the biggest on the physical layer, the biggest contribution to the network. We need to make sure that when we have a qubit, for example, in the left memory here, it needs to be entangled with qubit on the right memory, and we also need to know that they are entangled. And in the remaining of this talk is basically how can we do that? How can we, from a network perspective, make sure that we have kind of entangled qubits in our memory? So the first one, it's a little bit of a deviation, the naming conventions from the literature, but I try to explain it. So here we have the sender-receiver method. So basically we place the photon source at one side of the kind of communication partners. We let a photon shoot into the atom qubit that is usually in memory, and we also prepare here a second qubit, I think in the Hadamard basis. Then with this interaction on the left side here, we should get an atom that is entangled with a photon, and this photon is traveling to the other side, so basically a flying qubit. And then hopefully the photon interacts then with the atom on the right side, and then we should have entanglement. Important, we need to also focus on the classical communication. So currently, this is how I understand it, a lot of the classical communication that you have to do is kind of self-built. So the messages that are sent are basically just what the current research or research lab is needing. And for really large-scale quantum communication, we need to have kind of a standardization. So meaning when you're talking with, for example, another lab, the number or which bits, classical bits represent what, need to be standardized standardized, and everybody needs to basically talk the same or a similar language at least. And this is what we call in networking, at least, protocols. And this is what basically the main focus is here. Yeah, we sent this packet back. Also with some additional information. So, for example, what is the other communication side here? Maybe also was it successful or not? And how many attempts did we have? Because usually this is just here one example. Usually we want to parallelize this a lot. So we have multiple sources at this side here, and we need to generate like multiple entanglement at the same time. For example, with multiple fibers that we're having, so we can kind of do the multiplexing with multiple fibers at the same time. So this is kind of the second one, the two photon source method. Here we place a two photon source in the middle, which can create entanglement photons that are entangled, so two photons that are entangled. Obviously, this doesn't work for example, a free space. Communication network that then for at this time, this is basically a mirror of the first method, because this time the travel time is reduced, obviously, at least for when you place it in the middle. But also you have kind of then twice the interaction probabilities. So this kind of has maybe a lower probability of success compared to the first method. But yeah, this is also kind of really hardware depending. So for example, what kind of detectors are you using? Are you using threshold detectors? How good are the sources, and so on. But yeah, then we have basically a similar method. We need to again exchange some classical information here in our terms packets, and we need to compare that, because what can happen is that maybe on the left side here, the photon interacted with the atom, but on the right side maybe not. And this is what we need to communicate, right? So that the left side here knows, okay, we cannot use this qubit at a specific memory location because it's not entangled with a qubit on the other side. Then we come to the Bell state measurement one, and the Fock state method. That's how we call them. Here we kind of have a similar setup again as the first one, but we place a Bell state measurement device in the middle. We shoot again two photons this time into the middle. They are entangled with atoms in the memory. And then hopefully both photons arrive at the Bell state measurement device. Then again, this Bell state measurement device has to send some information again, which photons interacted or not, and then this is how we can have entanglement. In I'm not the Fock state one, but in the Bell state measurement device, we basically want to have like two qubits arriving at the Bell state measurement device. In the Fock state one, only one. So basically, how the atoms here are entangled is kind of different depending on the method. This is kind of a very important idea that I'm proposing. We need to structure our memory. How the qubits, or we have kind of a memory at a location, and we need to kind of separate them into these send and receive memories. Why? Because this kind of allows us to do full duplex communication. Because now when we have, for example, entanglement from left to right, we're only using entanglement from the send memory and the receive memory. And then when we go from right to left, for example, we only use from the send and to the receive. So they are basically then separated. Again, this can be purely logical. So we have kind of a full memory, for example, in a physical sense, but kind of logically we say, okay, then only the first n qubits are for the send memory and the remaining ones are then for the receive memory. Again, this is kind of a little bit problematic or to show here in terms of is it useful or not, but when you do when you do simulations for large-scale networks, this comes kind of the key player here. This is what we have to also then integrate into the packets or the classical information that we're sending around. So yeah. Then let's come to the combined L1 and L2 protocols. This is how we would represent on the networking side of things a protocol. So here in these blue nodes basically represent the L1, so entanglement generation, what we call it, and then the L2 is usually purification. So or any other form of fidelity improvement that we need to do for our qubits so that they're usable for long-term or long-range communication. So usually we start here with a check. Do we have enough qubits in our memory? And then we immediately go into this L1 generation here. So we start to generate qubits with one of these methods. And then we get this classical information back, and then based on the packet, we need to decide, again, this is here in this L1 check, we need to decide, okay, do we have enough do we have enough qubits that are ready for purification or not? When we don't have enough, we need to generate again. Again, this is also depending on the memory size that we're having. So we cannot just simply repeat the number of qubits that we previously had, but we need to kind of do this based on the memory. And then we go into the purification. Again, purification requires us to send information from A to B and also from B to A. So this is what we then detect here as a packet. And then we need to check was the purification successful or not. Again, if we don't have enough qubits after the check that are purified, then we have to go back to the L1 generation. What can happen, this is quite important for purification, it can happen that we receive a packet from one memory that the other side already purified, but we didn't. So we have this also then this kind of separating of the states in terms of what we need to do. Because sometimes results, we need to compare these results that we have. So one from our measurements or our purification that we're doing and the one from the other side that we're getting. So both need to be present. And it could be that either ours is present and we're waiting on the other side, or the other side is present at our location, but we didn't do any purification yet. So this is why we have this, this separation here. Let's come to our simulation. We had like a really simple setup, 2 nodes, communication link. We modeled that as an optical fiber, and we let the distance basically between these 2 communication partners, we let that run from 5 kilometers to 50 kilometers in these discrete steps. Then we had the number of sources. So how many attempts can you do in parallel? This infinite here basically just means we can do every attempt or the number of qubits that we want to establish all at the same time. It's always a finite number, so it's not infinite. Then we had on our quantum memories, we had a T1 and T2 error, so depolarization and dephasing error, and we let that run from 1 millisecond to a second, so to see how long do we need to be able to store our qubits so that we have kind of meaningful results. Then we kind of, this was kind of a parameter when to stop the simulation, how many qubits we want to have in our memory after the purification. It's 2 to 5. And then also we set our memory size. Usually for purification on the low end, you need twice as many that you want to, that you need to store, because purification uses like 1 sacrificial pair, and this is kind of the lower bound. The upper bound we just set arbitrarily at 3 times the requested qubits. And also in this kind of the important one, we had also an unlimited memory, so to see what happens when we have kind of a really huge storage. Again, when we're talking about, for example, 5 qubits, unlimited would also be like in the terms of hundreds or so, just to have kind of a comparison. The thing is, we developed some models for the sender and receiver protocol and also the 2 photon source protocol that I didn't discuss here. But for the BSM and the Fox state, we had some models, or there were already existing ones. And what we showed here, or what we compared here, is the runtime. So basically, how long do we spend time in the simulation calculating the models, and how long does the simulation actually take to see, okay, are these models efficient enough for large-scale communication? Or at least for the simulation, that we don't have to wait like a lot of days to simulate like a very simple case. And as we can see here, we have quite the low low runtime. So we are here in, I don't know, some milliseconds compared to when we simulate that stuff into the hundreds of milliseconds. So this is kind of a good sign. These models are fast, so that we can use them for large scale simulations. Let's focus on the delay. This is kind of the very key metric for us in networking. So how long does it take to run these simulations, or to establish entanglement? These perfect conditions here just means we have all of the physical parameters, for example, the fidelity of our quantum sources, also the duration, also the dark count of our detectors. We set them basically to the optimal value. So, for example, fidelity should be 1 in a photon source, or the dark count probability should be 0. And to see, okay, what are the raw statistics that we can get. And here you can see the sender receiver protocol, and performs quite well. Also the BSMP and the FSP perform really good, whereas the two photon source doesn't perform, or because of the overhead that you have in the communication, they perform quite similar. But this kind of changes when we then introduce like real hardware parameters. Now we have, for example, in a photon source, we have now not a perfect fidelity. And there you can see, because of the current state of the art of this two photon source model, the delay is quite high because we have like a low success probability. So we have like a lot of retries in terms of entanglement, and also the quality, which we show then later, is also not as good as the other ones. But this is just purely based on the hardware. Then let's come to the memory size. This is quite interesting what it does. In the perfect conditions, it actually increases in terms of delay. This is basically because we need to handle more qubits at the same time. Whereas with this limited capacity or limited memory size that we have, we just remove or reduce the number of qubits that we have to address at the same time. But in the realistic conditions, again, this is the more interesting case. This is where we actually see quite a significant change when we go to basically a huge memory size. We make our entanglement generation really more consistent. So the variance in terms of delay is really hugely reduced when we increase the number of qubits that are available in our memories. Let's come to the fidelity. Under perfect conditions, or important, this black bar here is just saying, okay, what is this threshold for purification? In the, I think, experiment which was shown, they basically said, okay, fidelity has to be above 0.5, then we can run purification. And in terms of coherence time, or mostly here, this is the dephasing time. 1 millisecond is not enough for any kind of length that we're having, which shows that most of the qubits are basically having a fidelity of 0.5, and quite also a large chunk then has below 0.5, so they are not usable for any quantum communication. And only increasing this the coherence times kind of increases the fidelity of our established qubits. Again, under perfect conditions here, so we don't have any hardware degradation. But important is, again, increasing from 100 milliseconds to 1 second doesn't really do that much in terms of fidelity increase. And this is also what we see in the realistic conditions. So basically there is a trade-off, or we have to kind of set our memory coherence times. We're just purely talking about entanglement generation to a value that kind of is dependent on the length that we have. Obviously, the longer our communication needs to be, the higher our dephasing time has to be. And this is kind of shown quite nicely here. Again, these low of the 2 photon source here are mainly due to the hardware parameters. Yeah. Got any questions?
Perhaps I have an addition. Perhaps you can add something about the simulation platform you have made and also make it available for other people. Perhaps you can say something about that.
Yeah, so the simulator where we implemented all of not only the models, but also this classical communication and so on, this is basically developed by myself. It's open source. So just write me an email and I can give you access to it. It's very important to notice that it's kind of only doing the physical simulation, like the physical, what is going on the physics side of things, only on a pure model-based method. So I don't want to have, or the simulator focuses mostly on the communication side of things and kind of tries to model the physics or the underlying physics of qubits, decoherence, and so on, like on a very model-based simulation, so that we have kind of a fast simulation. But yeah, I'm happy to also kind of have improvements to these models that we developed here. So yeah, feel free.
I would also have one question. The purification protocol, maybe I just skipped my attention, but did you use a specific one?
I think we used the one proposed by Zeilinger. Like you have your 2 entanglements, right? So one on the left, one on the right, and then you perform a C0 between the source pair and the sacrificial pair on both sides. Then you measure the sacrificial pair, and then you have basically a 0 or 1, and this is what you communicate to the other side. When they coincide, so when they're both 0 or both 1, then basically you have successful purification. So you have a fidelity increase. If they're basically not this, when they're different, then you have to remove both of the qubits, or both of the entanglements that you have. Yeah, but this is kind of some for the future. This is what I'm currently implementing. Like really, because this is like a purely physical quantum memory. So we have like one cold atom or one trapped ion, for example. What I want to implement or currently implementing is really a logical quantum memory. So we have like multiple qubits that represent one logical qubit. Again, we need to be fast with the runtime. So we just model the process of error correction and so on, just on a single density matrix, and not kind of, we don't simulate the whole code, for example. Like when we have 7 qubits in your code, we don't have a 2 to the 7 density matrix, 7 qubit density matrix, yeah.
If I give you the layout of this network I showed yesterday in my talk, would you be able to compute the fidelities, delays, and everything for entanglement distribution between all the nodes?
Yes. So basically, each of the nodes in the network has basically their own time, and with kind of a easy event routine and simulations, we kind of synchronize this time, and then you can easily kind of not only calculate the delays or the time that you have, but also the fidelity. This is kind of important. We have density matrices, right? And with the standard formula, I think you can easily calculate also the fidelities. So yeah. And this is what you see here, like when we're calculating here, for example, the fidelities of something, is like really, we have the optimal. So for example, the belt state, the first belt state, and we compare that to the the density matrix that we have in the memory, and then you get this fidelity value. Yeah.
Okay, so then if we have no further questions, we thank Benedikt again.